Hello, thank you for coming and welcome. My name is Jason White with the Optimal Robotics Lab under the FAMU FSU College of Engineering. Today we are going to review a force-based control of bipedal balancing on dynamic terrain with Tallahassee Cassie. In the real world, legged systems will encounter various terrains with unknown properties, whether it be a surface with unknown spring and damping constants, or slippery terrain where footholds can easily be lost, or even a rigid terrain that can unexpectedly collapse, like standing on a pile of branches and sticks. We wanted a bipedal standing controller that reacts rather than plans and responds to rapid dynamic changes. In robotics, there are a wide variety of methods used to control legged systems. Here we see some impressive results from a few of those control schemes. On the top, we see the Wabian 2R using a modified zero-moment point controller, Atlas using a centroidal dynamics controller, and Duris using a multi-body model-based optimization. On the bottom, we have Mercury utilizing the full dynamic model in an operational space controller, and Cheetah 3 using a model predictive controller. Another method of control, called force or torque-based control, uses a much simpler approach. To the right, we see the Toro robot. This 25-motor humanoid system can remain upright on soft terrain. When perturbed, the pelvis acts compliantly, but the whole body maintains its stability. When the system is placed on a moving substrate, we see similar results. Throughout the video, the humanoid remains standing on these challenging terrains. We investigate developing a similar controller, but wanted to respond to more rapid changes and impacts due to alterations in foot contact in something we call dynamic terrain. So what exactly is dynamic terrain? To answer this, let's first consider the legged system seen here. Pretend the system is standing on a rigid asphalt surface. A common practice would be to use joint position control to make the system stand. However, if this system were to encounter a terrain that is slippery, moving, or can quickly give way, such as a rock slipping out or sand, joint positioning techniques would likely lead to the system toppling over. This type of non-rigid, rapidly changing surface is dynamic terrain. One way to control bipeds on dynamic terrain is to use a force control approach. By choosing a point on the system and commanding forces, we are able to keep the biped upright even when the ground isn't rigid. To ensure this method is a viable approach, we need to test our controller on a legged hardware platform. Lucky for us, we have Tallahassee Cassie, which is the focus of all simulated and hardware experiments in this paper. Cassie series robots are designed and built by Agility Robotics. The robot contains 10 motors indicated by theta and 4 spring-loaded passive joints. The computer operates at a 2 kHz rate and constantly monitors the state of the robot using joint encoders and an IMU. Cycloidal gearing at 8 of the 10 motors allows the user to command a torque and receive a very similar torque at the output shaft. Knowing the complexity of the hardware, we wondered if a simple standing controller could make it stand and remain standing on dynamic terrain. We begin by looking at the general controller design. Our simple standing controller assumes the entire weight of the robot is located at the pelvis, and we focus only on controlling the pelvis position. Now we know assuming the legs are massless isn't even remotely true, but we wonder if we can get away with this assumption. This general formulation also eradicates the need for a detailed multi-body model. We also wanted our controller to be reasonably tolerant to foot position changes so it can work with dynamic terrain. Using the displacement of the pelvis from its center with a simple proportional derivative approach, we developed desired forces. Multiplying these forces by the system Jacobian translates them into individual motor torques. Here we can see the specifics of the initial control structure. The weight force offset was split evenly between the 2 feet. The pelvis errors were multiplied by both Jacobians to get a total of 10 torques. Now the following videos show the hardware response. For this first one, keep your eye on the pelvis and how it moves. Watching closely, we can see the pelvis has an induced roll about its center as it is moved from side to side. The changes on the following slide focus on keeping the pelvis, or the black portion of the robot, from rotating about the world frame. Pelvis roll refers to the motion shown in red. To prevent this behavior, we modify the control signal sent to the two motors circled here. These two motors are responsible for pelvis roll. Using the IMU data and trigonometry from the feet location, we are able to determine what angle the motors must be at to induce zero roll about the world frame. This change modifies the control structure as seen at the bottom. Note, there is also a yaw correction in the control block, which leads us to our next modification involving the feet. When the Z rotational errors about the pelvis were zero, no torque about the Z-axis was applied to the legs. This allowed the feet to rotate freely and would ultimately cause the system to fall over. Instead, we use the kinematics to determine the feet yaw relative to the pelvis heading and develop individual feet errors based on those values. Testing the controller again, we see there is still instability associated with the controller, this time in the lateral direction. Although the pelvis has almost no roll, it moves freely from side to side with virtually no resistance. To resolve this issue, we notice that an additional vertical force at one side of the pelvis will tilt the system in the opposite direction. So to change the current pelvis Y position to a new desired Y position, we redistribute the weight offset force between the feet to drive the pelvis to one direction. Typically, this would induce a roll. However, our previous changes prevent this. Modifying the weight offsets in this manner is called center of pressure control. We implement this controller on the hardware, and dynamic terrain tests are performed in the following slides. Here we simulate the ground moving beneath Cassie's foot horizontally. The white dot represents a desired pelvis position, and the blue dot is the actual measured position. We can see the controller manages to roughly track the desired pelvis position as the foot slides. Overall, the foot slides approximately 50 centimeters from its original position.
Camera's on.
Next, we look at raising the foot from the front. We can see the controller allows us to lift the foot up, but keeps the pelvis relatively in the same location. The oscillation from the impact have since been fixed using the invariant Kalman filter developed by Ross Hartley and Jesse Grizzle's lab at the University of Michigan. Now let's look at raising the foot from the side. Again, the controller is not preventing me from lifting the foot, it only attempts to keep the pelvis centered and at the same height. At approximately 30 centimeters, we see the foot slip and regain its footing before the system once again becomes stable. In this final sequence, we remove the terrain from underneath the foot in what we're calling a box drop.
This time you'll notice there's no safety tether.
3, 2, 1.
Now let's watch that from a different angle. Now we'll rewind the footage and show it at 1/8 speed. Note how the foot falls on its toe while it maintains balance and eventually regains its footing. All is an emergent property of force control.
Overall, we successfully developed a standing controller which functions on hardware and uses only knowledge of its weight and kinematic model to calculate torques. The controller also keeps the robot upright when faced with a number of dynamic terrain scenarios. This is not to say the controller has no limitations. When both feet or a single foot were placed on soft foam, the system would either fall over or take a significant amount of time to stop swaying. We plan to further investigate if this behavior is related to a narrow foot surface area. However, we suspect that the previously mentioned Kalman filter should help with these results. Our current and future work is focused on extending the force-based controller to stepping, developing an additional controller by using operational space control, and further implementing the invariant extended Kalman filter. I want to thank the Mechanical Engineering Department at the FAMU FSU College of Engineering for their funding and support which helped make this research possible. I also wanted to thank the undergraduate research assistant Dylan Swart and my advisor Christian Hubicki for their assistance and continued support on the work presented in this paper. Below is a link to the originally submitted video to ICRA which accompanied this paper. Thank you for your time, and I hope you enjoyed my presentation on force-based control of bipedal balancing on dynamic terrain with Tallahassee Cassie.